in fact, Sunday afternoon, October 2nd and 4 p.m. So it's time for an exam to review in this lovely year of 2022. So a couple of general things as we get started. So for general exam procedures, they are the same as exam one. So by now, y'all have all had one exam. So you by now know that we will pass out the Scantrons. You know you need to do your Scantron in pencil, Not all of you did. For exam one, pencil. Pencil's what we need. You are in the same exam rooms. So the exam room you went to before, those exam rooms are still posted to the top of the course homepage. We'll send them all out again, but you are in the same places you were before. So I know that was concerning for the first exam, but you will be in the same places you were before. So same rooms. It is still 10 o'clock Saturday morning. Don't be late, be on time, be early. So those are your general exam procedures. So again, they are going to be the same for every exam. We are still editing the exam, so I don't actually know how many questions there are. So we aim for somewhere between 26 to 32 multiple choice. I don't know where it'll actually land, and 2 short answer. So that general idea of multiple choice and short answer will be the same. So we are aiming for 2 short answer. I don't actually have a clue how many points that'll be worth yet. We have not started those conversations. Bad news with Sunday afternoon. There are some things I do not know yet. One other thing I did want to touch on is stuff that you actually need back from exam one. So there are things that we essentially put to rest. Now keep in mind that the final, which is not until December, but the final is cumulative. So when I say you won't need this, I mean you won't need this until the final. So everything from exam one goes to the final because the final is cumulative over all of the stuff. But when you start to think about, okay, have an exam, about 7 days, what from exam one might be useful, this is when we can focus. So we can focus on things like electron configuration, because in exam two, we're doing electron configuration now of ions. So exam one had electron configuration. Exam two has electron configuration of ions. So we're using the same base information, and we're going to take it one step further to use it for ions. Same thing, we have things like ionic radius, where we talked about atomic radius before. Ionic radius builds on that concept. We also have a periodic trend of electronegativity, which is very closely related to electron affinity. So while it is a new trend, it is heavily related to things we did before. The other things from exam one to remember are your grams to moles conversions. And we'll do some examples of those. Grams to moles conversions, as well as dealing with moles now to molecules or formula units. Whereas this used to be moles to atoms, we put all of those atoms together now. So now we can go from moles to molecules instead of just moles to atoms. But that idea of those mathematics, how you came about all of those, where you pulled those numbers from, either the periodic table or the potentially useful information page, all of that you still need again. Just to reiterate, so those are things you do need. So just to reiterate some things that we won't use until the final. Are things like wavelength of frequency. So any of these formulas we were using, we won't use until the final. So we don't need to worry about frequency and wavelength, and we don't need to worry about energy to frequency, and we won't be doing the change in energy being equal to the various algebraic flavors of this thing. I know there was a whole bunch of algebraic flavors of that. So we won't use those until the final. So don't don't set your exam one on fire. I understand some of you have already lost yours, but don't burn that yet. The final is cumulative, but we won't use any of that stuff until the final exam. But there are some topics that build essentially from there. So those are my general announcements to start off with. Anything in the chat yet that might be on the more basic side? Chat.
First question we have here are there any formulas we need to be aware of?
Cool. So the thing with formulas, always a good question to ask, first of all. Always a good question to ask. The odd thing is there is math on this exam, but they're not things that I typically consider to be formulas. But let's go ahead and take a look at what we do have. So as far as calculations for this exam, we have things, there's different ways to describe this. So we can call this molar mass. Sometimes we call it formula mass. Sometimes we call it molecular mass. But essentially what these mean is they mean something like, whereas before, so in the before time, exam 1 time, we had atomic mass. And so for atomic mass, you would say, okay, I have something like an atom of iron, and we would go to the periodic table, which I have over here, and we would find iron right there, and we would get the average atomic mass of iron, 55.85. And so we could say, aha, I've got the atomic mass of iron off the periodic table that is 55.85. And this could be in AMUs, but we could also talk about this as being a unit that we could actually hold in our hand and talk about that being a certain number of grams per mole. So that's what we did before. Now, instead of dealing with iron, now we're going to deal with something like iron 3 oxide. So now it looks like that. So I'll go ahead and name that. So we're going to practice lots of different things. Iron 3 oxide. So in order to do a molar mass calculation, we need to take into account the fact that I don't just have a single atom of iron. I have 2 irons at 55.85 each, and I have 3 oxygens. I will scroll up in a minute, but for better or for worse, I have that mode memorized. You still get a periodic table on the exam, so the periodic table you do have on the exam, but 16 is a really, if you use it enough, you just kind of wind up learning and remembering the molar mass of the atomic mass of oxygen. Which you don't need to know. You get a periodic table, but in case, just in case. So we can add all those together. So 2 times 55.85, 3 times 16, add all of those together, we get 159.7 grams per mole. So this is one of those times where, to me, you can think about this as a formula if you would like, because you are still remembering to take in those subscripts into account, that I have 2 irons, I have 2 oxygens, I multiply with the subscripts, and then I add everything together. So there are mathematical steps to doing a molar mass calculation. There are, but it's not like one pretty equation to remember. So that's always the issue that I have with that one, is when we're trying to think of like, what are we doing and what's going on? These are not necessarily like really pretty things. We could do, so another math thing, granted that was always something a little bit different, but I have these numbers. Since I have these numbers, I'm going to use these numbers. So we can do molar mass, formula mass, molecular mass. The other thing we can do is we can also ask you for percent composition. This sometimes is also called percent by mass. And so because we've already done all of this math already, I'm just going to say, what if I wanted the percent mass of oxygen in, no, let's practice. Let's practice in something like sodium phosphate. Plus I haven't gotten to throw in a polyatomic ion yet, sodium phosphate. So it's more language. So if this is my question, then I need to know what percent by mass is. Percent by mass, you can think of this one as a formula because we want oxygen. So this is essentially the mass contribution of an element that we care about because the problem tells us so, all divided by our molar mass. And since it's a percent, we multiply it by 100%. So we need that total molar mass again, somewhat unsurprisingly. So I've got my formula up there because they gave me a formula. So I need sodium, I need phosphorus, and I need oxygen. 4 times, that one's 16. I'm again going to go to my periodic table. Sodium is 22.99. Sodium's right here. 22.99. Phosphorus over here is 30.97. Nine, 30.97. So I get all of my additions in there. I'm actually going to do these all one by one. So all of my oxygens together. So 4 times 16 is 64. 1 times 30.97 is 30.97. 3 times 22.99 is 68.97. And then I add all of these together. And I get 163.94. So this is my molar mass. So up here, my little formula, that is the bottom part. Then the top part says the mass contribution of an element. So the question asked for oxygen. So therefore, when I'm thinking about how much does oxygen contribute to the mass of a compound, I care about this big 64 number because I care about how much does the oxygen give me out of my total. So I'm going to use the total contribution of the oxygen divided by its molar mass times 100%. And that's going to give me the answer to this one. So this one kind of has a formula. Closest thing I think we're going to really have to a formula. 39, give 3 digits, percent oxygen. And this technically is by mass. But we can do other things. So one of the other things we can do, so far we have done a molar mass calculation. And we did a percent composition question. And I mentioned when we first got started that we could deal with moles. So, but let's go ahead and make this interesting. We're going to use some of the information we already found. What if I wanted to know how many sodium ions are in some number? Let's go with 5.2 grams of, and we're going to use the compound we already solved for. We're going to save ourselves a little bit of work. Sodium phosphate. So how many sodium ions are in 5.2 grams of sodium phosphate? So this question should kind of remind you of the time where we were looking for atoms. because this is set up in that same general way where we're asking for ions. So we're asking for something really, really teeny tiny. We're asking about individual sodium particles, teeny, teeny, tiny little things. But they gave us grams. And if we want to talk about teeny, teeny, tiny little things, we're probably going to need that Avogadro's number that is hanging out on the potentially useful information page. If you haven't already done so, you can go ahead and take a look at that 2019 exam that's posted to the 701 section to go ahead and take a look at it. Because that back page that has potentially useful information will look about the same that it did on your first exam, but that means that we didn't take anything away. So essentially, we always just add things. We don't take things away. So we're going to go ahead and start with the 5.2 grams. And this is of sodium phosphate. So that's stuff that we were talking about earlier. So because we're doing grams, or we're pretty sure we need Avogadro's number for this, I'm going to go ahead and go from grams to moles. When I do this, I'm still in sodium phosphate. So we started off with sodium phosphate, so therefore I need grams of sodium phosphate. I know the problem talked about ions, but I can't necessarily break this 5.2 grams down into individual ions. So what I'm going to do is I'm going to come back up here because I would like to use this molar mass that we already solved for. So we already solved for the molar mass, so that's what we're going to use. The molar mass of sodium phosphate, 163.94. So yes, I am cheating a little bit since we already solved for that number. So yes, I am using that again. So that's how many grams in a mole. Then I could go ahead and say, just like we used to do for exam 1, that in 1 mole of sodium phosphate, I could have 6.022 times 10 to the 23rd units of sodium phosphate. So that means that I have 6.022 times 10 to the 23rd sets of 3 sodiums and 1 phosphate. So that is essentially a repeating pattern. So this would be similar to if I was trying to talk about something like, I do have it with me, your textbook. But when I'm talking about having 6.022 times 10 to the 23rd of your textbook, technically your textbook also has things like a front cover and a back cover and pages on the inside. So in a similar way, that sodium phosphate has 3 sodiums, 1 phosphate, 4 oxygens, just like your book does in fact have pieces to it. I will not rip your book apart. I need that. But that's not what the question asked me for. The question didn't ask me for units of sodium phosphate. The question asked me for sodium ions. So we got rid of grams and we got rid of moles. And now I have this, and I just have units of sodium phosphate. Well, what I know is thanks to this little number 3 down here, I know that in 1 unit of sodium phosphate, I actually have 3 sodium ions. So this is the new part. I understand that since we also did molar mass technically for the first time in this review, like 10 minutes ago, that the molar mass can also count as a new thing. But otherwise, the rest of this setup is stuff that you did on exam 1, starting with the whole thing, using the periodic table to figure out how to go from grams to moles. You did that on exam 1. Saying that I can go from moles to little tiny pieces. On exam 1, they were atoms. Now they are either molecules or formula units. This is an ionic compound. I know that because sodium is a metal. So now this is a formula unit. So then I can go from my formula units, and this is the new part, breaking down the formula unit and saying, I actually have 3 sodium ions in one of those, so I add a step. So this is another one of those times where some of y'all might very well have formulas to go from grams to moles and moles to grams. I don't. I just use the railroad tracks or the frames, and I make certain that I'm canceling out my units as I go along. So I personally don't have a formula for this. I understand some people do. So if you had a formula that worked really well for you before, you're welcome to memorize it again and use it again. But again, I personally am used to just making the units cancel and doing conversions as I go along. Final answer 5.73 times 10 to the 22. Oh, and this is sodium ions, pardon me. Sodium ions, or I can just forget that, Na+. 2 more? 2 more. So before I do anything else, any other questions so far? I just did a lot of math.
All right. The next question is can you please explain ionic characters? It was related to one of the end chapter questions in chapter 6, but I'm still confused by the concept.
Okay. Then let me do ionic character in just a minute. I'm going to put that up here. We can definitely do ionic character. But let me go ahead, if there's no questions over the math, let me go ahead and do my last math problem. I know I said there was kind of 2. Yeah. Okay. Last mega math problem. Because the last math, anyway. Math thing number 4. A sample contains, we're probably hoping we wouldn't do this one, 68% vanadium. The rest is oxygen. What is the empirical formula? Boom. That's all you get. A sample contains 68% vanadium. The rest is oxygen. What is the empirical formula? That's the entire question. That's all you get. And a periodic table. I'm really good at pushing that periodic table. So here's what you do. So for the record, this question is percent composition backwards. That's actually what this is. This is also useful because this, essentially exactly this, is a lot of times what you get when you do certain forensics work, because they'll give you back the element composition. But it's easier to get composition of metals a lot of times than it is of oxygen. So this, it's just like it's worded, really not that different for different forensics work, because they'll be like, cool, you have vanadium and there's oxygen in there, good luck. So the first thing we want to do, since we know there's some oxygen, we want a number for that. This is in percentage. So I'm just going to say that 100% would be the total. So I can go ahead and subtract the vanadium percentage from that to get the fact that I have 32% oxygen. So that's my first step. Then what we're going to do is we're going to go to a mole ratio. But I have percent, and that's weird. The problem just tells me I have a sample, and it doesn't tell me what the mass of the sample is, which means I get to choose. And I know that's weird, but they didn't tell me how much the sample was. So I'm just going to choose a number in grams that makes my life easier. So you can pick a number that makes your life easier. For me, it's easier to just go ahead and assume that this is 68 grams of vanadium, and that therefore this is 32 grams of oxygen. If you wanted to, so I assume there's a 100-gram sample is what I do. If you would want to prefer that there is a 12-gram sample or a 1-gram sample or a 5,280-gram sample, you certainly can. And you can then take the percentages and get those values. But again, 100 grams makes the percent numbers really convenient, which I like. So now that I have numbers for this, I'm going to go from grams to moles. That's what I'm going to do. I have vanadium. That's fun. Where's vanadium? Right here. A big V. It's like I prepared this question on purpose. I'm also going to need the oxygen, which is hanging out over here still at 16. So my atomic mass for vanadium is 50.94. My atomic mass for oxygen is 16. I'm going to use both of those values to take each one of my now gram values. So for vanadium, I am dividing by 50.94 grams in a mole to get 1.33 moles vanadium. For oxygen, I'm dividing by 16. Gosh, this makes my numbers look so pretty. This part I actually did not do on purpose. I just hadn't picked vanadium in a while. So I have now ratios. So I'm actually going to keep going in the way that we're quote unquote supposed to. There is perhaps a follow-up question you could ask me. Now my oxygen's a nice pretty round number right now, which is cool, but the vanadium is not. So usually these numbers look worse than this. This example just happens to have really pretty numbers, but usually these numbers look worse. So usually what we do now is we go ahead and we divide by the smallest number. So usually we go ahead and we divide by the smallest number. That will force us to get a whole number. I know we already have one, but we're going to assume that we didn't. So that would get me a 1 for the vanadium and a 1.5 for the oxygen. Now I have my other number with a whole number. So this is the part, I'll address the stuff in blue in a minute. But this down here is the part where we do expect you to recognize the fact that 0.5 looks a lot like 1/2. So what we're going to do, and if we had 1/2, if we multiplied 1/2 by 2, we get a whole number back. So we're going to take everything in the subscript and multiply it by 2. So I'm recognizing that 0.5 looks like 1/2, and therefore I'm going to multiply everything by 2. So I get V2O3 as a final answer. So that's how that one works. Now, two things. One, if when I said obviously 0.5 is 1/2 and you were like, no, it's not obvious, I don't know what you're talking about, your calculator, which I understand that this is too small for you to see, but your calculator, like the one you have that we force you to use on exams, not some magical other calculator, the one we make you use, actually has a button on it that looks like this. F and an arrow and another arrow and a D. This button is a fraction to decimal button. So if you type in 0.5 and then this button, your calculator will spit back out at you 1/2. So if you don't like fractions and this whole notion that 0.5 is a half, and you're like, that is not obvious, I don't know what's happening here, your calculator will actually do that work for you. It will. It would be nice if you knew that 0.5 was a half, but I understand that not everybody loves fractions. So your calculator, the one we forced you to buy, both of them have this button. I know I only showed off the X2S, but both of them have this button. So one more thing. What if the number's not pretty? Or so some people, when we got to here, might have been like, oh, look, 0.33. 0.33 is another fraction I know. So some people might have gone ahead and done this one. And multiply this by 3. You can do that. You get V4O6. This is the part where you have to remember the question called for an empirical formula. This thing, the thing we boxed before, this is what we call an empirical formula. This has the lowest ratios that you can have. So 2 and 3, they're both prime numbers. Aside from 1, you can't divide them by anything. Doesn't work. These are the lowest whole numbers that we can possibly have. If we'd done it the other way, and we got V4O6, that's not an empirical formula. V4O6, both of those are even numbers. So I actually would have needed to fix this and divide them both by 2 and get myself back to V2O3. So just remember that there is a definition for the word empirical. We don't use it very often because a lot of things come as empirical formulas, but we certainly can still do this as an empirical formula. One more math thing, and then we'll talk about ionic character. So if we had something like, actually, sorry, this was the one that I remembered as I was going along, so I did not pre-prep this one, which is unfortunate for me. But we will just do something with lots of carbons and hydrogens because that'll work for us. So if I tell you that the empirical formula is CH3. So this is the start of a new problem. Empirical formula is CH3, and the molecular mass is 30 grams per mole. What is the molecular formula? So this is another thing where you can think of this as a formula itself, but essentially what we're asking is an empirical formula gives you the lowest ratios. The molecular mass that they gave us is for the whole thing. So this number, this 30, is for the whole thing. This CH3 is just the smallest piece or building block. So what we're going to do is we're going to go ahead and solve for the molar mass of CH3. So this is one of those times where I am just going to pull these numbers from memory because I have them memorized. Instead of scrolling back up to the periodic table. So I apologize that I am being a little lazy when I do that. But that is mostly because my periodic table keeps getting farther away the more of these I do. And so the scrolling sometimes makes people a little bit dizzy. So I am just going to go ahead and tell you what those are because I unfortunately have those memorized. I really wish my brain would remember people's names like I can remember numbers. Great with numbers. If everybody was a different like set of digits of pi, I'd be way better at everyone's name. But that's not the way the world works. So this is essentially my unit. My molecular mass is 30. So if this is the whole thing and this is the part, the question is what's the formula for the whole thing? So all we're going to do is we're going to take the whole thing by 30 and divide it by the part that I have. This should get me a whole number. It's not going to be exactly a whole number. It's going to be 1.995. This is awfully close to 2, you may have noticed. And since we're asking still for whole number ratios, since my original is CH3, what I'm going to do is I'm going to take my CH3 that they gave me, and I'm just going to multiply all of that by this number that we solved for. So this final answer for the molecular formula becomes C2H6. So that is another math thing that you can do. And keep in mind, this one, it is still a math problem, but it is predominantly a definitions question. So the actual concept behind this is knowing what an empirical formula is, knowing what a molecular formula is, and then doing a little bit of math on the side. So that's predominantly what those are. One more formula. Actually, I'll tell you what I'm going to do. I want to answer that person's question. So what I'm going to do, because there's 2 more formulas, but they're both in chapter 6. So what I'm going to do is I'm just going to write down what they are. So the 2 formulas that I have not talked about yet, but since there have been questions in the chat that I've just been completely ignoring. What am I doing? Formal. Talking to myself. Formal charge is the other one. And then there's also a formula for bond order. And I guess you could say there's a formula for counting valence electrons because you add them all together. But valence electrons is the only other thing that to me has math in it, because you got to add a whole bunch of numbers together. And my class has probably already watched me add numbers with a calculator, because adding and talking at the same time, not a skill I have. So those are the other 2 formula things. That there are formulas for those 2 items. But someone wanted to talk about ionic character. So answer that question, because that person's been very patient while I did a whole bunch of math stuff. So ionic character. In general, when we talk about bonds, we have 2 types of bonds: covalent bonds and ionic bonds. So when we say covalent bonds, these are all about sharing electrons. When we talk about ionic bonds, these are all about charge-charge interactions or electrostatic interactions. So a positive thing and a negative thing, electrostatic interactions. So there isn't sharing in an ionic bond. It's all about how attracted are the 2 ions to one another. One of them is positive, one of them is negative. Maybe there are sets of them that come together. So maybe there's a couple of them that are positive and one of them that's negative. Regardless, they're all about charge-charge interactions. Covalent bonds are all about sharing sets of electrons so they can actually have stable octets together. So the whole concept of a covalent bond and an ionic bond are different things. But when we're looking at them, and especially when we're trying to talk about electron density, we often wind up with this idea of a spectrum. And on one side, we have something like a pure covalent bond where everything is happy. And usually these are things like the same element. So a hydrogen and a hydrogen sharing a set of electrons, or a fluorine and a fluorine sharing a pair of electrons, or really anything that's the exact same element. So we could also go ahead and put on this side of pure covalent 2 nitrogens, whatever you want. Type of bond doesn't matter, but pure covalent, evenly sharing, life is good. On the other side is ionic. So this is where we're back to 2 charges. So we could call that sodium and chlorine. We could call that calcium and oxygen. We could call that the one we did earlier and call this sodium phosphate. Point is that they're all charge-charge interactions. on this spectrum, we can talk about the distribution of electron density. Distribution of electron density. And over here on the pure covalent side, this is very evenly distributed. So completely evenly, that single bond that we draw in the middle, that's where the majority of the electron density of the bond actually is. Beautiful, perfect sharing. Over here with the ionic is not evenly shared because one of these things is positive, one of these things is negative. There are way more electrons where the negative thing is because that is a charged thing. So no matter what it is, we got a positive thing and a negative thing. They're separate ions. The electron density is way out of whack. It works for those compounds, but it's not evenly distributed by any stretch of the imagination. Now, I told you it was a spectrum, which means that there's stuff in the middle. And so somewhere in the middle is where we call these things something like a polar covalent. So this is where, and there's things all along this line, but the only one we really bother naming is a polar covalent bond, because otherwise we just describe how polar is the bond. So here now what we have is a hydrogen and a fluorine. And what's happening here is now we need to talk about electronegativity, because the bottom line here is that these are not evenly shared, but they're still covalent. So they are sharing, not like the ionic ones where like these are my electrons and those are your electrons and we're separate. Polar covalent, they are sharing, but one of these is getting more of the electron density than the other. I'm actually just going to get myself another periodic table, come to think of it. No more scrolling. What? Apparently I will scroll back because it was mad at me. Still want to scribble on this one. There we go. So in general, when we look at the periodic table, we again are going to continue ignoring the lanthanides and actinides. They are cool elements, but they don't fit the trends very well. So when we talk about periodic trends, fluorine is going to be the most electronegative element. All about our lovely, wonderful fluorine. Fluorine's the most electronegative element. And just like before, in general, that trend does go and just point to fluorine across. Some general things you should know is there is this idea that when we're describing this trend, it's like a backwards Z. So it's fluorine, then it's actually oxygen, then chlorine. As far as like what order are our most electronegative elements, then nitrogen, then sulfur. So it's this weird Z coordination of most electronegative. So fluorine is the most electronegative, but second place goes to oxygen. So most electronegative, definitely fluorine, don't get me wrong, but in a close second is oxygen. Hydrogen, not very electronegative. It only has, it's a very small element. It only has one electron. It gets bullied around by a lot of the other elements a lot of the time. Don't get me wrong, its small size is useful, but hydrogen's not going to be very electronegative compared to fluorine, the most electronegative. So fluorine is going to have most of the electronegativity, is going to have most of the electron density then around this molecule. So if I was drawing these and I was trying to describe the electron density, I would try to draw between hydrogen and hydrogen as perfectly symmetrical as I can. I'm not a computer. That is as perfectly symmetrical as I can. If I'm drawing hydrogen and fluorine, I don't want to be symmetrical now. I want to give as much electron density over to fluorine as I can. So this is me attempting to draw electron density as ellipsoid things. So a lot of times there are different ways to describe bonds and to describe that idea that things are not evenly distributed. So to go along with this idea, because as I've been describing this idea, I'm sure some of you are like, wait a minute, I've heard of this concept before, but that's not what we called it. My class is rolling their eyes. So we can talk about this as percent ionic character or just ionic character. We can also talk about this as polarity is another option we have. I've been using electron distribution or electron density. That also works. There's two more that I haven't even drawn yet. One is a dipole or dipole moment. And the other one is partial charges. Phew. For the record, this is always the reason that whenever I'm doing an exam review and people ask me like, is that all? I always make a face and I'm always like, I don't know. Because if you stop me and you ask me something like, can you name all 7 of Snow White's dwarves? I will confidently name 6 out of the 7 dwarves, and I'll get stuck on the last one. And then if you ask me an hour later, I will again confidently name 6 out of the 7 dwarves, and but I will have forgotten a different one and I will have remembered a different one. That's my memory. So I have different ways I compensate for that, but in this case, I think that's all of them. Pretty confident in class I came up with 5 different ways to mention this stuff. So the one I didn't mention yet, a dipole. So because there's more electron density to one side, we can actually basically draw an arrow for this and give this idea of a dipolar dipole moment. The fact that we can describe the fact that there is more negative stuff on one side on a regular basis, because that negative stuff is always going to be with the fluorine. So the fluorine will always have more negative stuff. So we can actually draw a dipole trying to show that there is negative stuff over there, less negative stuff on the other side. The other one I mentioned were partial charges. These are the ones that look a little bit weird, but they look like this. Highly recommend you take a look at your textbook when you take a look at these. But again, we're trying to just say one side has more electron density than the other. More electron density is going to mean more negative stuff, but they're not whole charges. So we don't just get to draw a negative sign where the negative stuff is and a plus sign where the negative stuff is not. We give these partial signs. In my handwriting, that is supposed to be a lowercase delta. Oh, I'm on a computer. Sorry, that didn't need to sound like it was so interesting. I can actually grab, there it is. So it's supposed to be a lowercase delta. So if I was doing this a pretty way, it would look like that. So there's the computer's drawing of what I was trying to do. So put that next to it. So for those of you curious as to how good my lowercase deltas are, oh. All right, that is percent ionic character. Other questions or questions over what we've covered so far?
There was a quick question I wanted to get before we get back to the order, but someone asked, could you leave it as a decimal or round, or would it be wrong?
So, as you guys have seen our exams by now, remember that for multiple choice questions, all of your multiple choice answers have the same number of digits. So your multiple choice selections, you don't have a choice, and we will not make you pick between 32 and 32.0. Those are the same number, and we only get 5 multiple choice options. I personally am not wasting a choice option on different versions of the same calculation. Not doing it. So the one thing I miss from online exams, I really missed lots of options. Okay, I can handle this. Other thing, you've already seen us ask you a calculation question on an exam, on exam 1. where we specified how many digits we wanted you to give us. We mostly did that so you would give us at least 3. Also, so that if somebody just puts down a number like 100 as a blind guess, we could be like, that's not enough information. So we will ask you for a certain number of digits. We're pretty lenient in general, but we ask for a certain number of digits, mostly so that if somebody tries to give us like the number 4 and the actual answer was like 4,000, we can come back and say, you need to give us more information. So short answer, you've already seen how we ask questions. If you have questions on the short answer grading, I'm happy to talk about that, but that's usually a better one-on-one Q&A, which I know I owe lots of people emails, but I drove to Houston this weekend, so I did not answer emails or other things so far.
The next question is, do we only need the info from 4.6 and 4.7 for the exam too?
So, grabbing my textbook, hold on. Because before I just answer that, I'm going to double check. So 4.7 is ionic radius. 4.6 is electron configuration of ions. So I had a question for you who is curious if that's all you need to know. If we ask you to give the electron configuration for silver plus, can you do that? Because that's fair game. I'm asking you for an electron configuration of an ion. I'm asking you for the electron configuration of silver plus. Now here's the deal. Here's silver. So if I was going to do the neutral silver, I would start with krypton. And then I would remember that even though the next thing I'm going to write is 5s, which is an electron configuration, silver is one of the 5 exceptions we asked you to learn back on exam 1. So the neutral form silver is 5s1 4d10. This is something that's not in 4.6. This is earlier than that. But we still expect you to remember this. So we do still expect you to remember the exceptions that you learned previously. So silver does in fact have that exception of that 5s1. To remind you, there were 5 exceptions we asked you to remember: chromium, molybdenum, copper, silver, gold. Those were the ones that all have 1 electron in their s subshell that we asked you to remember. So those were the 5 exceptions we asked you to remember. So if I want the ion of silver, whenever I'm making ions, I'm always going to remove from the highest value of n. I have 2 values of n here. I have 5 and I have 4. 5 is the higher number. This is a +1 charge, so I only need to remove 1 electron. +1, remove 1 electron. I'm removing from the highest value of n. So therefore, when I write silver plus, that is krypton 4d10, and I'm done. So I guess to answer the question, is this only stuff we need to know out of 4.6 and 4.7? I'm going to go with no, because we taught you more things about electron configuration, and you do still need to remember things like the exceptions. So depends on who writes the electron configuration question as to if we do that to you or not, but we can. We're allowed to. Other questions?
The next one is, do we need to memorize all of the organic and inorganic compounds?
So I'm gonna play a game with what I think that means. So when you say all, I always have a problem with what that means. So there are some things that you do need. So you need these. These are Greek prefixes. Oh, look, PowerPoint is also giving me great captioning. So you do need Greek prefixes. These you need. These, methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, decane. You do not need. We will not test you on these names. We will not ask. The only thing we would do is we may name this for you and then tell you what the formula is. So we could say, what is the molar mass of butane? Because you are going to go pick up butane to grill with. Actually, propane is what you grill with. Butane is what goes in little creme brulee torches. So you have a butane torch, and you need to refill it. What's the molar mass of butane? In parentheses, C4H10, butane. So we would give you that information. Other things we would also give you are if you need any of the functional groups. So this way you would know that like ethanol, the OL is actually tells you something more about the structure. Really, we leave things like this in the notes so that when you are in the lab and you're doing something in the lab and they have you work with ethanol or methanol, or you go and you get isopropanol, all of those things are terms that are used, but you'll actually learn them in organic chemistry later on. So those you do not need. That being said, things you do need. Dun, dun, dun. Polyatomic ions, table 5.10 out of your textbook. This list, which I can't even make, I can either make it so that the whole table's on one page, there we go, or I can make it big enough you can see it, but I can't do both. And I lost the fact that this is table. I double checked, it is still table 5.10 out of your textbook. This list you are responsible for. So these you do have to have memorized. So I don't know if this was in the set that you were considering, but these you have to have memorized. That was part of why actually earlier, like an hour ago, when I did sodium phosphate as an example, phosphate's on this list. Phosphate's down here. You know, you can't see it because it's too small. But so polyatomic ions you do have to memorize. So those you do need. But butane, ethane, propane, no. But polyatomics, yes. Polyatomics memorize, yes. Other questions?
We have 2 questions relating to the Lewis structure. Should I ask both right away?
Yeah, let's do those.
Okay. So the first one is, when drawing the Lewis structure, do we draw a valid structure or the best structure? Will the question specify? And there's also another one later on.
Okay.
That is, can you go over Lewis structures for polyatomic ions?
Yes.
Sorry to interrupt. There's now also a third regarding Lewis structures. They said, do we need to know functional groups when making Lewis structures?
Cool. This has both a short answer and a long answer. I'm sorry, I shouldn't laugh like that. Okay, so valid versus best. So the question should specify. I should say that the question should specify. But if you're drawing it, you should be going for best. You should always be going for the best Lewis structure. Now that being said, we do sometimes ask a multiple choice question that asks you about valid. So for example, we might do something where we ask you to find the valid Lewis structure for a compound, but it'll have a whole set of compounds. And so it'll have like water, and I'm just going to make some really short ones. So it'll have things like this, and there's my water, and it'll have a, there. which one's valid. And so we could do, so what you would do for these is we would count up our valence electrons, again, to avoid, I haven't done this yet, so we'll do a little bit of scrolling. So oxygen, 6 valence electrons, carbon's gonna have 4 valence electrons, hydrogens are gonna have 1 valence electrons. So when I say valence electrons, I am referring back to the periodic table, and I'm using those group numbers above it. We could do it with electron configuration, but you don't have to. So when I say valence electrons, I am going to be using those group numbers to help myself out. So I have an oxygen for 6 valence electrons. I have 2 hydrogens at 1 each. That's 8. As I analyze this formula, I've got 2, 4 in bonds, 6 and 8 in my oxygen. So there's 8. I should have 8 for my valence electrons. I have 8 in the structure. As far as my hydrogen goes, my hydrogens should only be sharing 2 electrons, and that's true. My oxygen should be sharing 8 electrons, 2, 4, 6, 8, and that's true. So this is a valid Lewis structure. Valid. We'll talk a little bit about BEST in a minute because someone wants to know about polyatomic ions. It's a great time to do BEST. Methane. Now, granted, some of you guys may be like, I don't know what she did. I did something quickly to make the point about not valid. So 4 for the carbon. There are 4 hydrogens, 1 each. This should also have 8 valence electrons. I have 2, 4, 6, 8, 10. So already there are 10 electrons here. So this is already not valid because that's already a problem. Other things I did wrong. Hydrogen has multiple bonds. Nope. Hydrogen cannot handle more than a single bond. Can't do it. Also, this carbon is only sharing 4 bonds, or only sharing 4 electrons, pardon me. Only sharing 4 electrons. So this does not have a complete octet. So this is not valid for a lot of different reasons. So we can talk about the validity of a Lewis structure and some of the things that can go wrong in a Lewis structure. So we can ask that question. When we want to talk about BEST, think about this for a minute. We're going to do, I will come back around to the functional groups when I will. But a Lewis structure for polyatomic will actually help us think through a lot of this. So I'm going to pick a polyatomic. I'm going to pick phosphate. Honestly, because it's the one I went ahead and drew out in advance. Because I mentioned this, counting and talking, not my best skill. So phosphorus is right here. 5 valence electrons, bunch of oxygens, 6 each. So 5 for the phosphorus plus 3 times 6 for each oxygen plus, hey now, what am I doing? Also writing down numbers apparently and talking at the same time, not my best moment. There we go, phosphate. For anybody curious as to how I survive in the real world, I use Excel a lot. Also, I don't usually talk and do math at the same time, except for my profession in front of everybody. Otherwise, when I focus, I don't talk. So there's my phosphorus, there's my oxygens, 4, 6 electrons, 6 valence electrons each, and this beautiful negative charge means I get to add 3 electrons. So don't forget your charges because that matters too. So here's 32 electrons. Then I'm going to put, so I'm going to put my phosphorus in the middle, oxygens to the outside. This is both symmetry preferred and my least electronegative atom goes in the middle. No atom left behind connect everything together. I just used 8 electrons. So I now have 24 left over. Then I'm going to put the rest of my electrons and fulfill octets. So I used all my electrons. I'm out of electrons. And as I look at this structure, I can go ahead and see that all of my oxygens look the same. Sharing 2 have 6 more, that's 8. And when I look at phosphorus, phosphorus is also sharing 8. So phosphorus has 8 electrons, it has a satisfied octet. Oxygen has 8 electrons, it has a satisfied octet. We would refer to this as a valid Lewis structure. But it's not the best one. I'll show you why. Not the best. Which means you have to keep going. Now, first of all, how did I know that? Well, we have to analyze it first. So phosphorus, what we're going to do now is formal charge. Hey, that thing I promised you, which I still keep writing the word. Come on, Steph. Erase. Formal. So, formal charge. There are a lot of different ways to talk about this formula. This is the one I usually do. Valence electrons minus sticks minus dots. The goal of formal charge is to analyze every atom in the structure for how many electrons did it bring to the party and how many did it wind up with. So essentially, even though we did this whole Lewis structure with all of the electrons being shared and everyone hanging out together and being friends, we're now going to pretend like they're not friends and we are dividing everything back up again. But we want to know what we started with. So when we started this whole thing, we're doing phosphorus. Phosphorus has 5 valence electrons, which also could tell from a periodic table. So that's a 5. Minus, it says sticks. 1, 2, 3, 4. Sometimes you see the sticks written as something like 1/2 of all of the electrons in a bonded pair. What they're doing is every one of these lines really is 2 electrons. So every single line is actually representing 2 electrons. And in formal charge, what we're now doing is we're now saying, all right, for every line, the oxygen gets one of those electrons in the lines and the phosphorus gets the other electron in the line. But honestly, it's just as easy to just count all of the sticks. So, or lines, whatever you want to call them. And it doesn't have any lone pairs. There's no dots around it. Well, I should do one of them, but no dots. So phosphorus has a +1 formal charge right now. The oxygens, the other one I want to do. Now, granted, oxygen, 6 valence electrons minus sticks, that's 1, minus dots. So I'm going to count every electron in a lone pair. So even though we call them lone pairs, and I would say oxygen has 3 lone pairs around it, right now I care about how many electrons that is. I am counting electrons. So that's 6 electrons in total. So oxygen has a -1 formal charge. I could do the rest of them, but all of my oxygens right now are the same. So all of my electrons have the same formal charge, which is a -1. So every single one of these electrons is a -1, and my poor little phosphorus in the middle is a +1. The idea that I have both negative formal charges and positive formal charges in the same structure tells me that this is probably not the best one. I should try to fix this. even though it's valid, like it is, it's not the best one. So I should try to make this better. If I try to make this better, what is usually going to fix this is to share more electrons. Phosphorus, scrolling back up again, phosphorus is hanging out in the third period. So this is the part where the third period matters a lot. So we can basically draw a line on our periodic table, and everything that's below this line can have what we call an expanded octet. So these guys are all expanded, potentially expanded octet. They don't have to, but they can. So everything in the third period or below can have more than 8 electrons. It is still technically a violation of the octet rule, but it's an allowable violation. Sure. So we still count it like it's a violation, but it's allowed to happen. It does happen in nature. It's going to happen right now. So what I'm going to do, I'm going to redraw this so that we can actually see what we're doing. Also, I really should have drawn the whole thing with the -3 because it has that. So my Lewis structure should have brackets and a -3 charge on the outside to denote the fact that the whole structure has a -3 charge on it. So what I'm going to do is I'm going to share more electrons. I'll make that look more like the letter P. There we go. So I would like to share more electrons. So all I'm going to do is I'm going to take one of the lone pairs off of one of my oxygens. I'm going to move it. I really should have done a different color. Different color. Highlight. Take this. I'm going to move it. There we go. So when I do that, and you don't have to redraw this, but I'm going to, because that way I can make this look a little bit neater. So you'll notice now that phosphorus has 3 single bonds and 1 double bond, is at least what it looks like. We're not done with this structure yet. So what we're going to, -3. So we're going to analyze our formal charges again. So analyzing formal charge on phosphorus, 5 valence electrons from the periodic table, -5 sticks, -5 single bonds, 0. That's a good sign. Now I have 2 different kinds of oxygens. So I'm going to label this oxygen A. I'm going to label this one oxygen B. So oxygen A, still 6 valence electrons. And now it has 2 lines, 2 sticks, and 4 dots for a 0. And my oxygen B, 6 valence electrons, 1 stick, 6 dots, -1. So good news, bad news. Good news, I got some zeros. Bad news, I still have a negative charge. Now here's the thing. I'm not actually going to be able to get rid of that negative formal charge. I can move it. So if I wanted to, I could actually keep going and I could share another pair of electrons. So I could go ahead and move that oxygen B we talked about. And I could go ahead and draw this, and phosphorus can handle this. Phosphorus is totally fine, even though it's got more negative stuff now. So let's go ahead and analyze this one. And we'll talk about why we're doing things the way we're doing things. So here's my phosphorus. Still 5 valence electrons, now -6. So this is now a -1. My oxygens, I have 2 now that are 6 - 2 - 4 for 0. And I now have 2 left that are 6 - 1 - 6. So I still have negative charges, negative formal charges, because my overall structure has a negative formal charge. I'm never going to get away from that. So I'm going to have negative formal charges somewhere. And it's definitely better that we have zeros now. So the fact that we've got zeros hanging out, this is better. So now the question we need to ask. So I've got 3 different structures. And so they're all valid because they all have the right number of valence electrons, octets have been met. This one is definitely not best because it's got both a positive and negative formal charge. So this one's not our best one. We don't like it. We can do better. So the question now is, how are we going to determine between the one that has one single bond to one oxygen and that has, or sorry, one double, blah, that has a double bond or has 2 double bonds. Also, this is hurting me a little bit because of resonance, these sentences are wrong. We'll talk about resonance in a minute. I'm gonna get there. But I need to pick between this one or this one. It's like an optometry chart. Is this one better or this one better? How we're going to decide is electronegativity. Essentially, what's happening is something has to carry a negative formal charge. The things carrying the negative formal charge can either be oxygens or oxygens and phosphorus. Those are the options. So between oxygen and phosphorus, the question now is which one is more likely to want the extra electron density? Which one between oxygen and phosphorus, so many scribbles, is more likely to go ahead and carry that negative formal charge? And when you look at the periodic table, what you should see is oxygen should be more electronegative than phosphorus. So even though when we're looking at a Lewis structure, it's like, they look pretty similar, my oxygen is definitely more electronegative. So oxygen is more likely to carry the negative formal charge. So when I'm then deciding between these two, this one here, because giving phosphorus the negative charge is not best. Not best. Even though it's valid, this is also going to be not best because we don't want phosphorus to carry the negative formal charge. We want oxygen to carry the negative formal charge. And this version here has oxygen carrying the negative formal charge and phosphorus being at 0. So that's how we do best Lewis structure. We do best Lewis structure based on formal charges. And if you have to decide, also electronegativity. We use both. I have 2 things left before I ask questions again. One is I kept mumbling occasionally that some of this talking about double and single bonds in the structure made me a little itchy. This is also going to give us our last mathematical formula. And I have not forgotten that there is another Lewis structure question that I skipped over. So I haven't forgotten. Okay. We picked the best structure. This is the best structure. I have scribbled all over it. This happens a lot. So I'm going to redraw it just so we can have this conversation. One. So the thing is, when I'm drawing this, even though I understand that I just went ahead and drew a whole bunch of oxygens and they all look like they're the same oxygen, they're not. Technically, this is an oxygen atom and this is a different oxygen atom, still oxygen, but a different atom. This is a different oxygen atom, and this is a different oxygen atom. So I have 4 different oxygen atoms. And it looks like this double bond is only attached to one of them. This is a lie. It's a lie. Now, what I'm going to do is I'm going to try to draw the truth. And then we're going to talk about what we actually expect you to draw. So the truth is because that double bond really could go to any of those oxygens. In reality, it does. But this is going to make the drawing look a little bit weird and difficult. But again, we're working on what is the truth. The truth is that instead of the phosphorus essentially choosing one oxygen to give special attention to, that's not the reality. The reality is that extra double bond character is actually ooched out over the entire structure. That's the truth. This is an idea that we refer to as resonance. The idea that that double bond, when we draw a Lewis structure, the double bond, we put it somewhere. In reality, that's not what really happens. Those extra electrons are actually smushed throughout the entire molecule. This becomes important for a variety of reasons. In the real world, this is why certain molecules are more stable than others. This actually gives you a lower energy for the molecule because the entire molecule is sharing those pairs of electrons. They're everywhere in the molecule. Whole thing is more stable. So, the lie. The truth. What are we going to do? We're going to do two things. One, we are going to talk about things like resonance structures. So if I asked you to draw all the resonance structures of the thing that we drew, oh, can I copy and paste? I used to know how to do this. Yes. Okay, good. Yes. Sorry, everyone. So I'm like, wait, OneNote is awesome. I remember this. I'm kind of wishing I had drawn a better picture, but that's okay. Yes. Okay. So obviously I get to cheat because I'm not going to redraw them all. So what we are going to do is I have my original, and then I could draw the exact same structure again, but now I'm going to not have that double bond on the top. I'm going to have that double bond going to a different oxygen atom. And then I'm going to draw my little double arrow again, because that double bond doesn't have to go to the right-hand side. It could go somewhere else. So I could also have drawn it on the bottom. But I didn't have to draw it on the bottom. I could have also drawn this on the side, on the left-hand side. Now, so all of this drawing seems really silly. But what we're trying to do is we're trying to describe the fact that all of these are equivalent structures. So we then can refer to these as equivalent resonance structures. Because if you'll remember, this was after we had found the best structure. So we found the best one, then we did all this. And I could tell you that there are 4 resonance, 4 equivalent, which I can't spell today, equivalent resonance structures. So there are 4 of them. So on an exam, we could ask you to draw all of the resonance structures, but we could also just ask you, if you found the first one, how many are there? Because that way you can draw them all out. If it helps you to go ahead and see what are all of my options, you can do that. Or if you can look and say, okay, that double bond could be in any of these places, there are 4 places for it to be. There are 4 equivalent resonance structures. We've been known to do both. But there's one more way to describe this. I know you're excited about that. The other way to describe this is with something called bond order. This is the last formula, at least the last one that I can remember today. All we're going to do for bond order is we're going to describe the bond. And the thing is, we're trying to get back to this idea of the truth. So we're trying to get to the idea that it's not one single bond and a double bond, but it's this one and a little bit bond. So to do this, what we're going to do is we're going to look and say, okay, I have 1, 2, 3, 4 spots or places where I could have electrons. So I have 4, we're going to call these electron domains, places where I could have electrons. I've got 4 of them, 4 bonds. Then on the top, I'm going to take into account what kind I drew. I drew 3 singles and 1 double. That's going to give me a grand total of 5 divided by 4, or 1 1/4. So this molecule that I drew has where the phosphorus oxygen bond has a bond order of 1 1/4. So that's the last formula, is the bond order formula. And all we're trying to do is describe resonance. So we would say that it has a bond order of 1 1/4. We would not actually say that it has 1 double bond and 3 single bonds, because it doesn't. So back to that idea that that first structure I drew is actually a lie. And the truth is the 1 1/4. So the truth is 1 1/4. The lie is this weird looking thing. That's a valid Lewis structure, but it's a lie in real life. So we use bond order to correct for what's really happening. Back to the question somebody asked me. Functional groups. So first of all, what a functional group is. A functional group is that thing I told you you didn't need. So functional groups are organic structures that we don't test on. But here's the reason why that person was asking this question. It's a valid question. So one of the things in here is one of our favorites. It's this thing. So it's called a carboxylic acid group. Turns out this is really common. How common is it? Ever used vinegar before? Carboxylic acid. So this group, COOH, has a specific structure to it. There's usually other stuff over here. So that specific structure looks like this. So as let me draw the lone pairs, draw the lone pairs. Oh, why not? We'll complete our octet with a hydrogen. There we go. So the thing is that honestly, out of all of these, the carboxylic acid is the most useful to know, because it would be the only one that you might see. You can actually get to this using formal charge. So formal charge will also tell you that this is the best structure. So you don't have to do this with memorization. You can do this with formal charge. But this is pretty much the only one that sometimes is nice to be like, oh, I've seen this before. That's a carboxylic acid group. That's what that looks like. The rest of those, either you would get to through formal charge, or even just the structure itself. So an alcohol group is OH, and that it looks like that. All you have to do is draw the lone pairs on. The amine group, which is NH2, the only thing we would make this look like is we give this its lone pairs and make the hydrogens like that. It's just the aldehydes would be something you would do through formal charge as well. So the carboxylic acid group's not bad to know, but you can actually get to that just through formal charge. You can. I ran out of questions. Other questions?
All right, I believe 2 more questions about Lewis structures just came in a little while ago. Next one is for Lewis structures, the least electronegative goes in the center. So is C or S more electronegative? And then the other one is when drawing Lewis structures for ionic compounds, is it preferable to add extra electrons if needed to the most electronegative atom or least electronegative atom?
Okay. So one thing at a time. So carbon versus sulfur. So carbon versus sulfur. So we start with fluorine as most electronegative, and then we go to oxygen next, then chlorine, then nitrogen, then sulfur, carbon. So we would say that sulfur is more electronegative than carbon. Not by a lot, likely, but that sulfur is more electronegative. You can also play that game by looking at where fluorine is on the periodic table and where the sulfur is on the periodic table. And go ahead and say that since sulfur is closer to fluorine than carbon, that sulfur is more electronegative. The other thing in general, carbon is best at sharing. So folks asked me at one point before the first exam, when we're talking about things like charges on carbon, or maybe it's after, anyway, after the first exam about charges on carbon, and we went ahead and we're like, well, carbon is going to be -4. They're like, yeah, but couldn't it also be +4? And it's like, yeah, but it's carbon. Carbon doesn't like to be charged ever. Carbon's likely to just share. So while you can answer this question about carbon versus sulfur with the periodic table, like I just did, and go ahead and say sulfur should be more electronegative. More electronegative. So you can do it that way. The other thing to consider is that carbon is not very electronegative. So if you just ever have to guess, you can almost always be like, yeah, not carbon. If they're both nonmetals, carbon's not very electronegative. Carbon's usually hanging out in the middle if it can. Carbon likes to share. It's really good at sharing. It's like the best at sharing. Best at sharing. It's not just good, it's the best. But you can do that from the periodic table as well. You can. So the other question, and I wrote this question mark for a reason. So talk about doing Lewis structures for ionic compounds, and the other question that went with this is, do extra electrons go on most electronegative element? So in general, things I like about this question. In general, if you have extra electrons, the more electronegative, there's two different things to look for. Either the more electronegative, like we were doing earlier and said, hey, if it's going to have formal charge, the more electronegative element gets it. But the thing to watch out for, if it's extra electrons, watch out if it's a strict octet. I will show you what I mean by that. So when we were talking about one of our structures, and I drew the line on here, so many lines, and I said, hey, if we're on here and we are looking at this and we are in the third period or below, we can have an expanded octet, no problem. The thing though is that you've got some elements that are, technically we can put neon in here, but neon won't form any bonds. These are 8 only. These guys are strict octet. They are 8 only. They will not do more than that. So if you're like, oh, fluorine's really an electronegative, I'm just going to give that thing some extra electrons. If fluorine already has 8 valence electrons, it's done. It is out. Quite literally. It's got an ion, it's done. So you can't break the octet of carbon, nitrogen, oxygen, fluorine. They cannot have more than that. They won't. They don't. You cannot do that. If this is the only thing you go into sophomore organic chemistry with, you will still be in good shape, because the number of people that draw 5 bonds to carbon make us sad. 8 only, strict octet. Boron is 6, beryllium is 4, hydrogen is 2. So there's some other weirdness with octets that we didn't talk about. But carbon, nitrogen, oxygen, fluorine, 8, only 8. I don't care how much it makes your life better to make them have more. They can't. They can't, they won't. The thing that made me curious about this, and the reason why I've got a question mark on here is because we can do Lewis dot symbols for ionic. But I wouldn't call these Lewis structures, because ionic don't really worry about octets. So if I'm doing a Lewis dot, I can think about sodium and the fact that sodium, back to my periodic table, I'll copy this so I can stop scrolling, make myself dizzy. Sodium, why are you mad at me? Every once in a while, I'm like, I understand that I am on a Mac using a Windows product, but come on, Microsoft. There we go. So sodium is hanging out in the group 1A, so it has 1 valence electron. So sodium plus should just be without that ion, sodium plus. And I could draw chlorine, then the chlorine, group 7A, Cl, 1, 2, 3, 4, 5, 6, 7. And then I could draw the chloride ion with its negative charge. Try to do this all in rows. The chloride ion then would have all those little dots around it, and we would go ahead and use the brackets to demonstrate the negative charge. So I can draw Lewis dot symbols for sodium and chlorine, and for the sodium ion and the chloride ion, I can do all of that. But we wouldn't really draw those lines in between them, because those lines mean that electrons are being shared, and ionic formulas, ionic compounds don't share electrons. So we wouldn't actually draw any lines between them, so we wouldn't really call it a Lewis structure. We call them Lewis dot diagrams, but usually don't call them Lewis structures because there's no sharing involved. Other questions?
All right, I believe the next question is there a list of acids we need to know?
I never know how well y'all can see my face. So, kind of. This is going to make you unhappy when I do this, but this is how I have to start this conversation anyway. So here's my list of acids. There's binary acids, and there's oxo acids. Oxo acids. Not oxo acid acids. Oxo acids. So as far as a list of acids you need to know how to name, there's your list. There's 2 of them. I know it's not what you wanted. I understand that's not what you really wanted. But this is the actual answer. Here's why that's the actual answer. Binary acids are ones where you have 2 elements, and hydrogen is one of them. So hydrogen and chlorine in water as a binary acid. Technically, so is water, which is weird. I don't like that one. I'm going to draw this one. So you're usually familiar with this top one. but we're going to name the bottom one in the same way. So this top one, HCl, as an acid, most people have heard of this before. Most people have used it either in a high school lab, you may have already used it in a college lab, or on a true crime podcast, I don't know, but it's hydrochloric acid. All we're going to do is we're going to take this idea, hydro and ic acid. And if you'll notice, the only thing I have left is the element. So because it's a binary acid and it only has hydrogen and one other element, you name all binary acids like this, where the only thing you flip out is the middle part for the element. So if I want to name H2S as an acid, I'm going to keep that hydro part. I'm going to keep that ic acid part from above. And then all I have to do is tell my audience that that's a sulfur in the middle and not a chlorine anymore. So this is hydrosulfuric acid. So those are binary acids. Because you can use binary acids with any one other element that makes a negative charge. So that would be the only other trick to this. So I need hydrogen and anions. I need negative charges to pull this off. That does mean that I'm stuck with a whole bunch of these guys. I think you can technically do it with arsenic. I'm going to go ahead and do tellurium too. I think you can do it with those. Don't remember. Some of these maybe. So if you really wanted to, you could name every single binary acid. There's not that many of them because there's not that many elements that form negative anions. But you don't need to memorize that because you probably already know hydrochloric acids, and then all you have to do is change out the part in the middle. So those are binary acids. Now, that's only one kind of the acids. There's another kind of the acids, oxoacids. These are some of the other ones you've likely seen before. So the one you've likely seen before is H2SO4, which is sulfuric acid. Now, you might notice that I already named an acid with sulfur in it, and that was hydrosulfuric acid, the one we did before. This one is just sulfuric acid. So this is a really small change, but this small change is enough to tell me, hey, I have oxygens. So it's small change, but that change is enough to tell me that I have oxygens. Now, the thing is, how did I actually get here? Because this is not a memorization game. I actually got here from this guy. This is sulfate. ATE ending. If it ends in ATE, that's where we swap it over to IC and acid. So ATE goes to ic acid. If I had the other polyatomic ion with sulfur in it, this is sulfite, SO3 negative 2. This is sulfurous acid. So it's similar. It's only a little bit different, but that goes with my ITE ending. So the main thing with your oxo acids are going to be to recognize the polyatomic it comes from. So all of your, and again, in a similar way, every polyatomic ion that you are responsible for, you can name as an acid. All you have to do is take whatever polyatomic ion it is. So let's say it was this one. and name it. This is hypochlorite. Then this has a -1 charge. The whole point of this acid is to be a neutral compound, so I only give it 1 proton, 1 hydrogen to go with it. And this now becomes hypochlor, but now where this ITE ending goes, I take that part away and I replace it with OUS and the word acid. So again, the original question was, is there a list of acids we need to know or need to memorize? And that list can be very short, which is binary acids like hydrochloric acid and oxo acids, which are based off of polyatomic ions. If you wanted the longer list, if you want to practice, all the binary acids come off the periodic table. Anything that makes an anion, binary acid, no matter what they are. If you want oxo acids, then you are in fact onto your list of polyatomic ions. So every polyatomic ion with oxygens in it, you can do. So you could absolutely take any of these and go ahead and add on enough hydrogens to make the charge balance, and you can go ahead and make an acid out of that. So you can actually still do, this is one of my personal favorites for this one is actually oxalate, because it looks like you can't do it because it looks weird and we don't use this one a whole lot. But I've got a -2 charge, so the original oxalate is C2O4 2-. So I have a -2 charge, so I need 2 hydrogens to cancel that out. And then again, I've got that ATE ending. All I'm going to do is remove my ATE ending. And then remove the ATE ending. OXALIC. Acid. And now that is oxalic acid, which, by the way, super important in cells. So oxalate, oxalic acid, definitely a thing that happens inside of cells. Totally a thing. And you can name it right now, even though we're not in biochemistry. You can name it with your list of polyatomic ions. I know, only I'm excited about that, but I'm excited about that. Other questions?
All right, I believe the next one is, do we need to know the common names of covalent molecules such as ammonia, or such as the common names of CO2, N2O, or even NaCl?
So there's a bunch of those in that list. So for common names, there are 2 you are responsible for. That is one that you probably already knew, but in case nobody ever told you that H2O is water, I am telling you now that this is a common name that you need to memorize. So if this is new information to you, that is okay, but I'm telling you now, we think you know that. So you need to know that one. The other one that is typically less commonly remembered or known, but we also would need you to memorize, is ammonia. So these 2 are common names. You have to memorize them. You have to know them. End of story. End of story. Some of the other ones that were mentioned. So these are the 2 you have to memorize. 1, 2. Other things that the question asked were things like, I think, NO2. We would go ahead and actually have you name this as nitrogen dioxide. It is super common, so you might even hear me occasionally call this one nitrogen oxide, but we would have you go ahead and name this one as nitrogen dioxide because that's what we taught you. That's what that is. So we would have you name that one as nitrogen dioxide. There's one more that the person that I definitely heard in that question, which was this one. This one, you're going to use your regular ionic naming for this. So NaCl, you are going to name based on your periodic table and what you know about naming. So just like, I did skip this over, but nitrogen dioxide, I've got nitrogen and oxygen, and those are both nonmetals. So I named nitrogen dioxide based off of covalent rules. NaCl, Na, there's sodium over here on the left, Cl over here on the right. Blue on blue highlighting is not good. Blue. So all I'm going to do is I'm going to use my regular ionic naming. Sodium is a alkali metal. As an alkali metal, it only has one charge option, so I do not need to use any Roman numerals. And then, so I just say sodium. That's all you need to know. And then chlorine, all I'm going to do is name the ion. So you do not need to memorize the name sodium chloride. You should be able to figure it out because sodium chloride is named with the regular ionic naming rules. So there's no reason to memorize it because you should know how to name any ionic compound. So that's not memorizing, that's practice. So yes, you had to practice enough to be able to do that. And to the beginning of that question's point, there are two common names to memorize, water and ammonia. Other questions, or were there other things in that list I missed?
The next one is, why is it iron? Yeah, why is iron parentheses 3 instead of another number? I don't know if this one's been covered yet.
No, because I think I did that pretty quickly. So I did this one, and I named it iron 3 oxide. If I had a different one, I could name it differently, and I'll show you why. I'm gonna, but first things first. One part of that question is, why isn't it something different? And it can be different, but something else has to be different for that to be different. So how do we get here? How do we get here? So iron is in here. Iron is in the transition metals, which means we don't know what its charge is because it could be one of a couple different things. Oh no, it's iron. What could it be? Multiple things. So this is the part where we never start with iron. We actually start with the non-metal it's attached to, or that it's attracted to, I should say, which is oxygen. So we're going to go and look at oxygen on the periodic table. And when we look at oxygen on the periodic table, it's hanging out in group 6A, and it is 2 away from neon, from a noble gas. So I should be able to know that oxygen is going to form a -2 charge. Left to its own devices as an ion, it wants to be an anion. It wants 2 more electrons. That's the charge it's going to have. So then when I'm looking at my structures, I know the oxygen is -2. I know that. That's the only thing it can be. It's the only thing that can be here. So oxygen has to be -2. So then I have to compare it with the subscripts. So starting off with perhaps the more straightforward one, over here on the right, my oxygen is -2. I have here that I have iron, just iron. So basically my oxygen is -2. This whole entire structure has no charge on it. So I need something in this box to cancel out the -2. That's going to be a +2. So I know from the fact that this is a 1-to-1 ratio that iron has a positive 2 charge. So that's how that one works. Oxygen's -2. You only need one thing to cancel out the -2 on the oxygen. Iron is also going to be 2, but positive. Get the Roman numeral 2 in the parentheses. When we're looking at this one, it's a little bit more complicated. Now, there's different ways to think through this. One of them is some people like to do what I refer to as a swap and drop, which is whatever number is down here, or whatever the charge number is, belongs as a subscript. So you can just undo that. Whatever number is here should be over here. So you can basically reverse the swap and drop and be like, oh, there's a 3 on the oxygen. The oxygen is -2. There's a 2 for the iron. So we just flip-flop these things. But the other way to think through this is essentially with the little algebra that I did before. We know the oxygen's -2 from the periodic table. I know that there are 3 of them and that the whole thing has to be negative. And this is the hard part. And I know there are 2 irons. So I know that if I'm trying to solve for my charge on iron, that there are in fact 2 iron ions. So then I can solve for this whole thing plus a -6 to equal 0, to x is equal to 6, x is equal to +3. Same answer. So yeah, so always a good question is, how did I know that? Always a valid question. And when you are trying to figure out the charges on a transition metal, what you need to do is you need to start with the anion. You need to start with the non-metal. You need to start with the thing that only has 1 charge. And then you have a combination of either kind of guess and check or thinking about those ratios to consider what the actual charge is on there. Other questions?
All right. I believe the next one is, do we need to know Coulomb's law? Or
So the hard thing for me is when anybody ever says, do we need to know Coulomb's law? Usually what you're talking about, usually what you mean by that is you usually mean, do we need the formula? Is usually what you're talking about. And Coulomb's law looks like this, where the Q's are charges, E is still standing for energy, and D here is distance. For us, this is between nuclei. So most people, when they say, hey, do I need to know this? They usually mean, do I have to calculate this formula? And that answer is no. No calculations with Coulomb's law. But if the question is, do we need to know Coulomb's law? You should be somewhat, Coulomb's law is a mathematical description of electrostatic interactions. So the idea here that positive things are attracted to negative things, and that the closer you are, the stronger the attraction. That part is fair game. So I guess the idea of like, do we need to know Coulomb's law? It depends on what aspect you're talking about. The idea that positively and negatively charged things are attracted to each other, opposite charges attract, yes, you should know that. The idea that the physically closer they are to each other, the stronger the attraction, you might not have thought about before, but that is also true. And actually, we've been using that when we did on exam 1, ionization energy. And actually, now that we're doing atomic radius or ionic radius, you can kind of see that as well, which is that the closer the electrons get to the nucleus, the stronger the attraction is. And that has an effect on things like the actual ionic radius. The more electrons you remove, the smaller that atom becomes, the stronger the attraction. So conceptually, I'm going to go with yes. Calculation-wise, I'm going to go with no. And it is 6 o'clock on the dot. So I'm going to say that the rest of the questions I can make a follow-up video for if you send me those questions. But since we are smack on 6, I think we're done. Unless there's something really quick in the questions that I don't know about.
I don't know how many more you'd want to go over quickly. I don't know how many of these would be pretty quick, but to respect your time, whatever you wish to do.
Well, let's give you one more. Why not? We'll do one more.
All right. So I believe the next one was if it asks how many sodium atoms rather than ions are in a 5.2 gram of sodium phosphate, is that the same thing?
So that's referring back to this question. So this is one of those times where I think I might have even done this in class, just to try to get away from having you guys think too hard about what's the difference between an atom and an ion. So I may have done this in class. In general, if we are speaking properly, which can be a big if we are speaking properly, we should call them sodium ions, because when they are in sodium phosphate, they have a positive charge. So when we're looking and thinking about sodium phosphate, this is 3 sodium ions being attracted to one big phosphate anion. So if we're using our words properly, we should call them sodium ions to reflect the fact that they have a charge. That being said, sometimes we, including myself, can get a little sloppy and just say, tell me about the sodium. I want to know about the sodium, and I want to know about the little itty bitty teeny little pieces of sodium, and so you might slip and call them atoms. So in that case, you can say that they're the same thing. Technically, they are not, so we should be using the word sodium ion because that's what they are. But if this problem instead said sodium atoms, you would do the same math. You would just be like, oh, they said atom, I've got 3 sodiums for every 1 phosphate. I am doing the same math. So yes, it's the same question, but saying sodium atoms is basically sloppier because at this point, we know what ionic compounds are. We know that in sodium phosphate, they are ions. They have a charge, so we should call them ions to match. But it's a good question. It's a good clarification question. Okay. Other things. How many more questions are in there?
From looking at them, it looks like we have about 6 or 7 more questions.
Oh, that'll take a good half an hour. So we'll go ahead and stop then. Because if there's 6 or 7 more questions, that'll take me 20, 30 minutes to do.
No worries. Well, thank you everyone so much for joining. I'm going to go ahead and end the live. This will be recorded, and Dr. Taylor said that she will be doing another video to answer the remaining questions. Enjoy the rest of your evening.